Remember at the end of week 2, we talked about how forces ultimately really are interactions between two objects. That's why we always have action-reaction pairs. Whenever one thing pushes on something, it pushes back. That's an interaction. We can also think of interactions in terms of energy. So energy is something that an object has, and how much it has determines how it interacts with other things. So if something has a lot of energy available to have an interaction, when it interacts with something else, it can have a big effect on the state of the other thing. If it just has a little bit of energy available for interactions, it can only have a small effect on the other thing. So you can kind of think of energy that way. So I'm going to go a little artistic on you and define energy as the currency of physics. The more you have, the more you can do. We will get more technical as we go, but I think that's a good way to start. Now, the way we're going to get through this is we're going to be defining different kinds of energy. So the first one we're going to work with is kinetic energy. And kinetic energy, I will go with the standard simple definition, is that it is the energy of motion. The energy of motion. So basically what we can say is that a moving mass has kinetic energy. Moving mass has kinetic energy. And I can show that with Hal. And what we'll see is that how much energy it has kind of depends on how fast it's moving. Okay? So if I have Hal sitting here, not moving at all, and I put my hand next to Hal, we can ask ourselves, what kind of an interaction is he having with my hand? Right? So Hal just sitting there does nothing to my hand. My hand doesn't feel any force, my hand doesn't move, nothing happens. Right? But if I let Hal have some velocity and it sits there, it hit my hand. I did a little drama and threw it back like I'm playing soccer or something, but you can see there was an interaction, right? So if I push him a little harder, it's a bigger interaction with my hand. So you can see that the ball does have some energy, some ability to have an interaction, and it's based on how fast it's going, right? So just imagine how big the interaction would depend on speed. So let's go ahead and give the formula. A moving mass has kinetic energy. How much? We're going to call kinetic energy K, and it's 1/2 mv squared. This is one to memorize. Kinetic energy of a moving mass is 1/2 mv squared. One great thing about working with energy rather than forces is that energy is a scalar. Yes, no vectors to worry about when you do energy. And you may say, okay, maybe energy is a scalar, but what about velocity? Velocity is a vector, right? That's a problem. Let's deal with that in a minute. I forgot to give you the unit, right? So K is 1/2 mv squared, and it's in kilograms meters per second squared. Kilogram meters squared per second squared, right? So that's the unit, or that has a special name. It's in joules. Or we just call that big J. So you'll see all your energy in joules or microjoules or some kind of joules. But in terms of other units, it's kilogram meters squared per second squared. Okay, getting back to this issue, it's a scalar. Velocity is a vector, so let's think about that. Let's remember the difference between velocity and speed. If I have Hal here and I free Hal to move around on the two-dimensional plane, we know that he might have a velocity with components both in the x and the y, right? We know that's the case. But v, the vector, is velocity. The magnitude, the amount of velocity he has, or just v, sometimes we're lazy and we indicate the magnitude by just leaving off the vector symbol, is usually called the speed. And is a scalar, because it's really just the vector without the direction information. So in this formula, notice we didn't say vector v squared, whatever that would mean. We said the scalar, we meant the speed squared. Okay? So that's what you use. So kx, the x component of the energy, and ky, the y component of the energy, makes no sense at all. We don't think about components when we talk about energy, because energy is a scalar. Okay? Also, k is always positive. Because even if you mess up and say, well, the magnitude of the velocity vector is negative, it can't be negative. The magnitude is always positive. But say somehow you decide to define the speed as negative because it's going backwards or something, doesn't matter, you're going to square it. Right? Mass can't be negative, half can't be negative, any number squared can't be negative because we're keeping it real here. So kinetic energy is always positive. So it's a positive scalar, no components. But keep in mind what it represents. It represents how much energy it has, and the energy goes up as the speed squared, how much energy something has to have some interaction with something else.